Let's start today's class. So before moving into a new topic, first I made a mistake in yesterday's class. So when we were we were discussing about the sensitivity analysis for this kind of a control system. And when so the first part was that you have to find out what is the transfer function, provided that this ds was your input and the reference input was 0. Okay, so we drew the we had drawn the equivalent circuit block diagram. What will be the case when we are dealing with TDS? So that time actually you told, I don't remember who, but someone told that the expression for theta 0 is by ds, which is equals to TDS, will be in the denominator there will be 1 plus k kt by rf into gs. So that was actually correct, but I made a mistake because that since here we have theta 0, but in the previous case you see that since theta 0 is now connected to the negative terminal, and even though theta r is equals to 0, that means the input to this this block Ka is not a positive, is not plus of Es. The input to this block is minus theta 0. So overall, even though in this comparator both the signs are positive, but still what the value of the variable which is being fed back to this positive terminal, that is a negative value. So that means in effect this will be a negative feedback system. So that means the denominator will not be minus, so it will be plus, which you said correctly. I made a mistake in yesterday's class, so sorry for that. So the take-home message here is that first of all you have to see what is the signs that are present on the error detector, and also you have to see whether the value or the variable which is being input, which is being compared at this error detector, whether that is of positive value or negative value. Depending on that, you will have either a positive feedback system or a negative feedback system, and accordingly you can write the transfer function. So is that okay?
Yes, ma'am.
Okay, so did you try to solve this problem?
Ma'am, no, ma'am.
Okay, but do you think you will be able to do it, or do you want to solve it now?
Ma'am, we'll be able to do it, ma'am.
Okay, fine. That's great. And the other part for so the first part of the question was that you have to find the sensitivity of the transfer function TD of S. The second part was you have to find the sensitivity of the overall transfer function TS. And in case of TS, what is the assumption here is that the value of DS is equals to 0. So you can find the overall transfer function and the sensitivity. And the third part was that to find the steady state error. Okay, so for finding the steady state error means the value of error at t equals to infinity. Steady state means at infinite time, whatever will be the value of the error, that will be your steady state error. Okay, so while finding the steady state error, so this so obviously you see that if you have if you know the value of ET, the error value in as a function of t, then you can find limit t tends to infinity, some ET will be whatever, that will be your steady state error. But there is if you remember that when we talked about the Laplace transform, there we had said something about final value theorem. So final value theorem. So that what did that theorem say? That if you have like limit t tends to infinity, some let's say ET in this case, that will be equals to limit s tends to 0 s into ES. Okay, so even if you don't know, see in our here you can find what is the value of ES. So for ES, so the steady state error, they want you to find the steady state error when DS is the input and the value of theta r is equals to 0. So similarly, from you can draw the block diagram keeping ES as your input and theta 0 So what will be the value of the ES? So from there you can find what is ES by DS, and once you have known that, so let's say here it's given that the value of DS is a unit step function. So unit step means DS will be equals to, so DS will be equals to, if that unit step is 1, so DS will be equals to 1 by S. So that means your value of ES will be nothing but, if you know ES by DS equals to something, let's say, and so that means ES will be equals to this some value into DS, which is nothing but 1 by S into whatever value you have already got. So that here you see that since you know the value of ES, it will be easier for you if you use this, the second part of the right hand side of this final value theorem, in order to find what is the steady state value of this error. So similarly, if you want to find out any the steady state value of not only the error, it can be any signal, it can be the steady state value of the output signal also. So similar way you have to find out what is the, either if you know the value of that variable in time domain, then you can do limit t tends to infinity of that variable. Otherwise, if you know the Laplace transform of that variable, then you can use this formula that limit s tends to 0, s into es. This will give you the the steady state value of, in this case this is the error, so it will give you the steady state value of the error. Now if you want to find the steady state value of this output, so then that will be limit t tends to infinity c of t. You can write limit s tends to 0, s into cs. So this will give you the steady state value of the output. So now we'll move on to a different topic. So this is in the module 2. So this is no longer in module 1. So here in this topic, basically we'll talk about the basic control actions which are present in a control system. So till now we have seen that you have a control system. So the control system will consist of, there will be a controller, there will be a plant or a process which you need to control, there will be some feedback mechanism. So these are the basic components of a control system. Okay, so as of till now we have seen controller as a black box. So we don't know what is actually happening inside the controller, or what type of what is the action which that controller is providing. Okay, so we'll talk about those basic control actions in this lecture. So first of all, just to recap what the advantages that a system has if we are using a controller. So the advantages are, first of all, by using the controllers, you can improve the steady state accuracy of a system. So by choosing a controller, by choosing a proper controller, you can decrease the steady state error of the whole system. The moment the steady state accuracy or the accuracy improves, or the steady state error reduces, that means the stability of the system also gets enhanced. The stability also improves. And also, if you use by using controllers, they can help in reducing the effect of unwanted offsets or unwanted signals which are there, like noise signals, disturbance. If you have a controller in action, so those effect of those parameters like this noise, disturbance and unwanted offsets, these things can be controlled, and the effect of these things on the output can be minimized as much as possible. Also, depending on what the type of system or the process that you are trying to control, it can be, so the process can be governed, it can be a first order system, it can be a second order system, depending on how it is connected. Using these controllers, you can, so if you have a second order system, then what happens if you we'll see that if you see the transient response of the system, so if you draw the output of a system with respect to time, so there you will see that for a second order system, mostly there is a large oscillation which is present during the initial stages. Later on, those oscillations, they die out and they become stable, but initially in the transient stage there is a lot of oscillations. So using these controllers, you can control what is the maximum oscillation, the maximum magnitude of the oscillation which is present in the system. And also it can be used to like speeding up or improving the response time of any kind of a system. So these are like basic advantages of using a controller. So now coming to the basic control actions. So basically the controller, it provides, the function of the controller is that it produces a control signal. So a control signal, or you can say that it is producing a manipulated signal. So that manipulated input is acting as an input to the plant or the process that you are trying to control. Okay, and this control signal which is generated by this controller, that depends upon the input which is generated by the by the error detector. So that means the actuating error, which is the difference between the reference reference input as well as the contribution or the part or the feedback path. The difference between that is my actuating error. So depending on the actuating error, a control signal is generated by some action in the controller. Okay, so this algorithm that relates the error, actuating error, to the control signal, that is known as a control action. So now there can be like different types of control actions. So the very basic type of control action is a two-position control action. So two-position control action means, so there can be either, it can be either on and off position. So it's sort of a binary kind of a thing. So it can be an on-off kind of a action. Then the second one can be that there can be a proportional control. Then we can have derivative control. You can have integral control also. And so these are like the basic control schemes. But usually when we have when you are given with a control system, so none of these control actions can individually control the system properly. So it might so happen that this proportional action is not suitable for, or this proportional action alone is not suitable for controlling the final system and making such making the system perform in such a way that the process variable is equal to my set point. So in that case, what we can do is that we can have a different combination of these proportional, derivative and integral control. We can have different combinations according to the to our desired output. So accordingly, you can have proportional plus integral control, you can have proportional plus derivative control, and you can combine all three of them together and come up with a PID controller also. Now let's see what a position control is. So as I have already told that the position in a two position control, the output of the control, it can have maximum one of the two values. So if you see this figure, so this is, if this is the controller and the output of the controller is empty. So the value of empty, it can have either can be equal to M1 or it will be equal to M2. So it can have only two states. Okay. So two states as in, so let's say if the error, actuating error, which is the input to the controller, that is greater than 0, then the output of the controller will be M1. And if it is less than 0, then the output will be M2. So usually in an on-off kind of a controller, this value of M2 is, so the most common thing is that the value of M2 is considered as 0. So if the output, if the actuating error is greater than 0, then the controller will produce it will produce sort of a signal such that, so the control element that is present in the next stage, that is open by 100%. So it's completely open. And if the actuating error is less than 0, then it will shut down so it will give a 0 output. So 0 output means it will shut down the next stage which is present. So in practice, basically this two position controllers, they have a so here you see that there is no hysteresis. So we are considering either 0 or 1. So immediately either it will be 0 or it will be M1. So depending on whatever is depending on the error signal. Okay. So but in case in practical scenarios, mostly what happens is that intentionally we a dead gap or a hysteresis that is being introduced into the system. So why we want a hysteresis? Ideally, we have always thought that, or we have already seen that hysteresis is something which is undesirable. We don't want any kind of hysteresis in our system. But now I'm saying that we are intentionally introducing some hysteresis or a dead band or a dead zone. So why is that? So to explain that, so here what is happening is that, so let's say this controller is now connected to let's take an example that it is connected to a control valve. Okay, so the output of the controller is the input to a valve. So what can happen is that when the output of the controller is 1, valve is open, it's open like 100%, and when the output of the controller is 0, so the valve is closed. So that means if your input variable is changing, the input is changing such that the controller output is changing very frequently. So that means the valve will be opening and closing, opening and closing. This action will keep on repeating multiple times. So that means this switching action of this valve, that will result in premature wearing out of this of that valve. So that means that from a mechanical point of view or from a financial point of view, you can say that the valve will stop acting properly after a few months, let's say. So in order to improve the lifetime of the switching hardware which is present in the final control element, we are intentionally introducing some dead band. So dead band is basically defined as a range or a value of set points, around the set point, so that when you have a control variable in that range, so here if you see, so let's say this portion is your dead band. Okay, so let's say this is D, this is your set point. Okay, so this is M1 and this is 0. So that means previously here you see that the dead band was 0. So the moment the error signal was greater than 0, it went to M1, and when it was less than 0, it came down to 0. But here, since you have a hysteresis or a dead band or a differential gap which is introduced, so that means if the value of error is lying between these two values, at that condition the controller will not generate, or it will retain its previous state. It will so the dead band is basically described as a plus minus to the set point. So if your set point is, so the dead band can be plus minus 1%, so on and so forth. Okay. So here you see that here it's explained in a better way. So this output M1, it switches. So this output M1, it switches to the output value MT, it switches to M1 only if the error the actuating error E becomes positive by at least D amount. Okay, so if E of T is greater than D, so here D is half of, so here let me say this is as 2D. So this part will be D. So if your error signal is greater than D, then the output becomes, the output switches to, it moves to M1. And when similarly it switches back to M2 when the actuating signal becomes less than minus D. So this differential gap basically it reduces even though it reduces the accuracy of the system, because here you see that between these minus D to plus D, when the value of ET is less than D and greater than minus D, in this position the controller is not providing any control action, any different control action. So whatever was there previously, it is maintaining the same state. So that means the accuracy of the control system obviously is getting reduced, but also at the same time the frequency of switching of the control valve, that is reducing. So that means it will result in a longer operational life. So you have to have sort of a trade-off between the accuracy that you need in a system and the and the mechanical longevity of your system. Depending on that, you can have lower value of, if you need a very high accuracy system and you are not concerned with the maintenance or the longevity of the switching hardware, then you can have a very small differential gap, or you can even have a very small differential gap. But if you have to if you can say that, okay, fine, I think I can my system can tolerate an inaccuracy of, let's say, plus minus 2% or 5%. In that case, by reducing the accuracy of my system to some percentage, I am improving the shelf life or the operational life of the whole hardware system. So then you will introduce a higher differential gap. So depending on what your requirement is, accordingly you have to select your controller. Okay, so now let's take this example. So here you have, let's say you have a temperature control system. Okay, so in this temperature control system, so what we are trying to do here is that we are trying to measure the temperature of the process, and the final, and how we are trying to control the process is by using a final control element, which is a steam valve. Okay, so this final control, so this steam valve, this basically in this system, basically there is a, let's say we have a 2-position control system. So that means the valve will either be fully open or it will be fully closed, depending on what is the input which is provided to the controller. Okay, so now if, let's say, the temperature, it falls below a set point. So let's say my set point is 100 degree centigrade. So now the moment the temperature of the process falls below the set point, so that means the valve will open. So the moment the valve will open, so that means more steam will be flowing into the system, which will eventually increase the temperature of the whole process. And now let's say the temperature of the process is slowly increasing, and so it will reach a set point of this 100 degree. So the moment it reaches the set point of 100 degree and it rises above 100 degree, the valve immediately closes down, and so that means no steam is coming into the system and the temperature is maintained. And so this process will keep on continuing. So in this process, the value of the control variable, that is fluctuating around the set point. Okay. So theoretically, this steam valve will have to like open and close continuously in order to maintain a constant speed or a constant temperature in the whole process. But obviously, if the valve is continuously opening and closing, so there will be too much wear and tear on the equipment. So in that case, we are introducing a deadband. So for example, if you are introducing a deadband of, let's say, plus minus 3 degrees centigrade, so that means if your so initially when the temperature was greater than 100 degrees centigrade, the valve was open, and the moment it was less than 100 degree, the valve was this was closed and this was open. So now after introducing a deadband of, let's say, plus minus 3 degree, so that means if the temperature rises beyond 103 degrees centigrade, then only the valve gets closed, and if the temperature falls below 97 degrees centigrade, then the steam valve opens. And between this temperature, 103 degrees C to 97 degree, in this temperature, if the valve was previously in an open condition, it will remain in an open condition. If the previous condition of the valve was in a closed state, it will remain in a closed state. So that means the system will not respond to any kind of changes in temperature between these 97 degree to 103 degree. So this plus minus 3 degree deadband we are introducing, but in this case, what we are doing is that we are reducing the number of fluctuations, and we are or the number of switching, and we are improving the longevity of the system. So here you see, if you see this figure, so the temperature versus time. So when the temperature, so this is the deadband which we have introduced. The set point here is 100 degree. So this deadband here, this value is 103 degree, and this value is 97 degree. So the temperature is increasing. So the moment it increases beyond 103 degree, so that means the valve will close. So the valve is closed means the temperature will keep on, then again it will try to reduce. and the moment it reduces below 97 degree, again the valve opens, and so this kind of an oscillatory response, oscillatory temperature characteristics will be found. So here you see that, so this red figure or the red plot is basically the variation of the temperature which is happening over time. So you can see that the temperature is not maintained at a constant 100 degree, but it fluctuates between 97 degree to 103 degree. So between that range, so it is with an average of, you can say that with an average of 100 degree, but it is not maintained at the value of 100 degree at every instant of time. Similarly, if you see another example where you have a level water level control system. So this is also a similar kind of a system. So you have, so this is the water levels. You have an inlet valve, and you have an outlet valve through which the water is flowing out. Fine. So initially the water level was 0. Okay. So what we want is that we want to keep the water level constant at a value of H. Okay. So initially when the tank was empty, so what we'll do is that in order to maintain that H level H, you will open this valve and water will flow into the tank, and the moment water is flowing into the tank and this valve is, let's say, it is also open. So there will be some water is coming into the tank and some water is going out of the tank also. So if the rate of inflow of water, which is Qy, is greater than the rate of outflow of water, which is Q0, then the level of the water in this tank will increase. So if you remember that we had seen that the differential equation of a single water level, liquid level control system is given by RC dH dt plus H into R of R into Qy. So H is basically the head or the water level, Qy is the inflow rate, and Q0 is the outflow rate. Okay, so from here you can see that this is a first order equation. Fine. So now let's say that after a certain amount of time, let's say at t equals to T0, we have achieved the desired level of water. So the moment we have achieved that desired level of water, so that means this valve will close and there will be no longer, so the value of Q0 will be 0. So value of Q0 is 0, but this so that means this now water will be draining out, because this outlet valve, that is still open. So even though the input flow has stopped, so that means since the output flow valve is open, so water will continuously keep on going out, so this value of H will reduce. So if you substitute the value of Qi, so let's say after t equals to T0, when the tank, when this input is closed, so at that position the equation will be RC dH dt plus H will be equals to 0. Now if you draw the curve for HT, so the rate of change of this water level, so this is the part when this is the filling curve. So filling curve means when the input water was flowing into the tank. So that means the condition was Q1 was greater than Q0. So in that case, you will have, if you solve this equation, you will find the value of HT is an exponential equation. So it keeps on increasing exponentially to this point. The moment it reaches this value, let's say H, which is the desired value, so then this input Qi becomes equals to 0, and slowly the water level starts reducing. Okay, so the water level starts reducing. This also, again, it follows a exponential curve, and it will keep on decreasing like this. Okay, now if the switch is adjusted such that the for a desired water level, the input valve that will be on and off, the position of the input valve will be either on or off depending on the difference between the actual water level and the desired water level, which is H. Okay, so what will happen is that, let's say now we have introduced a small differential gap. So initially, if there was no differential gap, so the moment there was a little bit, the value of this H reduces by a small amount, it will again the input valve will open, so it will again start rising up. So this will be very this will sort of continuously the switching of that valve will be there. Okay, so now what we are doing is that we are introducing a differential gap, let's say. So if the so in this differential gap means, so initially it is so it is filling up. Okay, so this was the first case when there was zero differential gap. Okay, so when you have a small differential gap, what will happen is that the moment it crosses this HD plus D, it will close the input valve and the water level will start decreasing. And the moment the flow becomes lesser than HD minus D, then it will again the input valve will open and it will again the water level will again rise. So there will be a continuous switching, and so for some amount of time the water level will come down, and then again the water level will go up, come down, go up. So this kind of a cycle will keep on continuing. So the effect of this differential gap is that if you have a very small differential gap, you see that you will have more number of switching which is present, but obviously here you will see that the output is the error margin in the output that is less. But if you have a larger differential gap, the error margin increases. So that means now the average or the accuracy of the system becomes even less, but the number of transitions of the input valve, the closing and switching on, that is much less. So accordingly, you will have to have a choice, or you will have to compromise between what is the whether you want a longer life or a longer shelf life of the control elements, or you want a more accuracy of the system. Okay, so this was all about two position control system. So now let's talk about something which is known as proportional control system. So basically these so before going to that, so all controllers, they have a specific use or a specific case where they are best suited. Okay, so you cannot just insert any kind of controller in any kind of situation and expect that you will get a very good result, and your output, the difference between your output and the reference input will be less, and you will get a very fast response time. So everything cannot be done by a single controller. Okay, so every single controller has their own disadvantages also. So in case of a proportional control, they work best if the deviation between the input and the output is not much, not very large. So if you have a small deviation between the input and the output, and provided the deviation is not very sudden, like instantaneously, let's say you are getting a change in the input and the output. If the error signal is changing instantaneously, in that case this proportional control is not a suitable option. So so what is proportional control? So as the name suggests, that the control signal which will be generated, that will be proportional to the error signal. Previously in the two position controller, we saw that the output of the control or the control signal which is generated, that has only two values, either a positive value or 0. But in this case, you can so the output of the controller, that is the control signal, that is directly proportional to the input which is present, the actuating error. So you can write that M will be equals to some constant Kp into the error signal, and this Kp is known as the proportional gain or the proportional constant. So now this value of Kp is generally kept greater than unity, because we would always want to amplify that, because this error signal is since we are dealing with small error signals. So if you want to use if you have a higher value of Kp greater than unity, so you will amplify the error signal, and that could be detected easily, and it would be able to drive the process or the plant according to your need. So this proportional control is basically, or essentially, it's an amplifier. You can assume it as like an amplifier with an adjustable gain. So in this block diagram, you see if this Kp is your proportional control, so the output M will be equals to Kp into this EA into S. So if you want to write the transfer function of this proportional control, so that will be MS by EAS, which will be equals to KP. Fine. So in this proportional control also, so there is one thing that which is very important, which is known as proportional band. Okay. So similar to the previous case, like in the two position control, we saw that we are having like this a dead band or a differential gap. So similarly, in case of a proportional control, we have something which is known as proportional band. Okay, so the proportional band means that it is the amount of change in the control variable that is necessary in order to get a 100% change in the output of the actuator. Okay, and so if you see that, so the proportional in this figure, you see that this is the control output, and if you have a set point at, let's say, so this is your set point. Fine, at set point, your controller is providing an action of 50%. Now, now your set point is your input is increasing. Okay, so if you have a narrow proportional band, so that means if your narrow proportional band means, so this is a narrow one. So you see that the change in or the difference in the control variable, which is necessary in order to switch the control action from 0% to 100%, that is less. So for a small amount of change in the control variable, you will get faster action. But if you have a wider proportional band, so that means that so that means in case of this thing, so the output, in order to change the, or in order to get 100% change in the output, you will have to have the control variable that has to it has to vary by a large amount. Okay, so we can say that the gain of the controller, which is given by KP, that is basically inversely proportional to the the value of the proportional band. So if you have a higher gain, if the value of KP is high, so that means the proportional band will be less. So KP is high means you can see that the slope, KP is basically nothing but the slope of this line between 0% to 100%, the slope of this line. So the slope for this line is higher. So here slope is less, and in this case the slope is high. So that means the slope, if you want to have a higher slope, higher value of KP, so that means the gain, the proportional band will be less. But if you want to have a lower, if you have a lower value of KP, then the gain of the controller, then your proportional band will be higher. So in general, so when do we need a higher value of proportional band and when do we need a lower value of the proportional band? So in general, if you have a lower value of this proportional band, that means what? That your system is responding very fast. So it is changing from 0% to 100%. The output is changing from 0%. The control output is changing from 0% to 100% in a very short amount of time. So the moment that short amount of time comes, so that means when you are dealing with a very fast response, there are chances that there will be some amount of overshoot. Overshoot means it will it might introduce some amount of sort of, you can say that some oscillations will be introduced in the system. But then again, if you have a lower or if you have a larger value of this proportional band, then obviously the system or the control action will be very slow. It will slowly keep on increasing until it reaches the set point. But here there won't be any offshoot or overshoot, but the system will be slower. So this is like again the trade-off between a higher gain proportional action and a lower gain proportional action. So in this case, you see that if you have in this figure, so you have a set point, and if you have the proportional band is narrow or you have a higher gain of the proportional controller, then the signal goes like this. There is an oscillating signal and the output of the controller, that is the control output, that actually there is an overshoot. It goes beyond the set point and then it keeps on oscillating, and maybe slowly if there is a damping, the oscillations will keep on reducing and it will reach the set point. But in case if you have a very wide proportional band, in that case the system will be very slow to respond. It will slowly keep on increasing, and finally it will try to reach the set point. Okay, so for example, if you have a proportional band of 20%, so that means a proportional band of 20% means here we see that gain is given by 100% divided by the value of proportional band in percentage. So that means the gain will be 5. So if you have a 3% change in your error signal, so error signal here means the difference between the set point and the process variable. So a 3% change in your error signal will result in a 15% change in the controller output because of this proportional action. But now if you increase the proportional band to 50%, so that means the gain will reduce to 2. So that means that for a 3% change, for the same amount of change in the error signal, the control's output will only provide a 6% change in the, there will be only a 6% change in the control output. Okay, so this is the, in general, the concept of a proportional band. So you can see that if the proportional band, if you make it as 0, so if you make the proportional band as 0, so that means it will become, it will rise very sharply. From 0 to 100, it will be just a vertical line. So that means it will represent a on-off controller. You can say that a proportional controller with a 0 proportional band is equivalent to an on-off controller. Okay, so there is one problem with, so if you have this proportional controller, so you see that if you have a small change, then it can, if you can play around with the value of Kp, you can select the value of Kp in such a way that the system is not giving you much overshoot, and the response time is also within your acceptable limits. Then you can use a proportional control. But using a proportional control, there is some problem also. So the problem is that usually when we use a proportional control, it is not, there is always an offset which is present between the set point and the control action. So that means that with, so there will always be, even at the steady state condition, the proportional action, after the proportional action, whatever the control signal that is generated, that is not able to reach the set point even at steady state also. So there is always a difference between the set point, so which is this, and the steady state value of this proportional controller. Okay, so that state, that offset is a major drawback of proportional control. So this proportional control is basically, you have, in order to have a proportional control, you need to have some positive value of the error signal. If the error signal is 0, so that means the controller will not provide you with any control action. So it will not give you any control. So there always has to be, in order for a proportional controller to work, there always has to be a difference between the set input and the controlled output. Okay, so and this the amount of offset which is there, which is introduced in a proportional control, which is present, that is basically dependent on the so if the offset, you can increase the, if the proportional band of this proportional P controller is higher, then the offset also becomes higher, and if the proportional band is less, then the offset becomes less. So this, as you can understand, that this offset error is something which is an undesirable characteristics of a proportional control. Okay, so obviously, if you want, if your system cannot accept any kind of offset error, so in that case, only using proportional control is not going to help. So either you have to use something else in a like in combination to this, and so that you will get a you can reduce this offset error. Okay, so now let's say that you have, let us say that now you have so this is your, so this is your proportional controller, and this is the system that you want to, or this is the process which you want to control. So the output is CS, input is RS. Let's say this is a unity feedback system. So this is plus minus, this is ES, and the output of, so here if you analyze this system, so here what happens is that, so if you write the, so CS by RS will be equal to, right, so you can just substitute KKP by 1 plus tau S plus KKP, right? So this is your, so this is the output, so transfer function of this overall system. Okay, so now let's say that your input, so RS is an step input. Okay, step input means that it is changing instantaneously. So this is the step input. RT. So it is immediately, there is a instantaneously it is changing from 0 to some given value. So let's say that value is equals to some A. So RT is basically equals to A for t, let's say greater than 0. So this is at t equals to 0 point. So that means the value of RS will be equals to A by S. So from here you can write that CS will be nothing but K into KP divided by 1 plus tau S plus KKP into A by S, right? So here we are having a sudden and sustained change in input, you can say. Okay, so now if you want to see the what is like why this offset is coming, this is just to show you. So from this equation, so you have CS equals to, so now what you can do is that if you want to find the value of CT, so CT, you for CT what you need to do is that you have to take the inverse Laplace of that of CS. So that will give rise to, so I'm just writing the final expression. So you can do the inverse Laplace of the previous equation and you will come up with KKP into 1 minus e to the power minus ST by tau 1, where the value of tau 1 is equal to tau by 1 plus KKP. Right, so now if you want to see that in case, so now offset error means what? That at infinite time, what is the difference between the set input or the set point and the output? So the output is now CT. So that means if you want to find CSS, so CSS will be nothing but limit S tends to 0, S into CS, or you can also write limit t tends to infinity CT, right? So you can see that at t tends to infinity, the value of so this offset at this will be equals to, or the offset error you can say, offset error will be difference between set point minus the steady state output. Okay, so the set point is A and the steady state output is given by this term will be equals to 0. So the C at t equals to infinity is nothing but A KKP by 1 plus K of KP. So that means this is equals to A by 1 plus KKP, right? Now you see that this value is always greater than 0. Right, so that means that even whenever you are using a proportional control, there will always be a difference between the set point and the steady state output. The steady state output of the system will never be able to reach the set point using only a proportional control. But here you see that if you increase the value of KP, if you increase the value of KP, so that means the value of offset will decrease. but then this might lead to higher oscillations in case of higher order systems. Okay, so and if you want to find out what is the like this, yeah, so this is like when you have but if you reduce the value of Kp, the offset value will be more and the oscillations will be less. So now the advantage is that this kind of proportional, so this value of Kp you should be choosing, there should be a trade-off. So you have to choose the value of Kp keeping in mind that what are the requirements that your system needs, or what are the requirements that needs to be satisfied. So you have to see what is the stability condition, or how much accuracy of the output response you need, what is the transient response, whether you can accommodate, like you can withstand, your system can withstand high oscillations or not. So these are the parameters which need to be considered for selection of Kp. So if you have a higher value of Kp, so in general that is determined, so the performance of the control system is improved, but since it leads to more oscillations, so there can be instability. So instability is basically due to oscillations. Now, but if you have a lower value of Kp, then obviously the corrective action which is being provided, that will be very slow, and you will have a slower, the response time will be higher, the response time will be more. So usually you need to do a compromise between while selecting the value of the proper Kp. Okay, so and if it is not possible to use this controller action, proportional control action only, then you have to incorporate some other, like some differential or integral, depending on what kind of need you have. Accordingly, you have to incorporate or modify your controller, incorporating other kind of controls also. So mainly the advantages of proportional action, control action is that it is very it's very simple and it's very easy to design, because it is only sort of as I have told, that it acts only like an amplifier with a variable gain. You just have one parameter to change. So you can either have a high gain or you can have a lower gain. So it's very easy to, or construction wise, it's very easy and simple to design, and also it provides good stability. Then if you have an overdamped system which has a very slow response, it can be improved up to some certain extent by using a proportional control. But the major drawback of this proportional control is that because of this, using these controllers, we will get, and definitely there will be some offset which is introduced in the system. So if your system cannot accommodate these kind of offsets, then only using proportional control, that is not going to satisfy your criteria. Fine. And also using proportional controls, if you have a higher order, if the plant is not of first order, is not first order plant, it is a higher order plant, then using proportional controllers, there is a chance that the maximum overshoot might increase while using a proportional control. So next we will see, in the next class we'll see what all the other types of controllers, that is the integral control and the proportional and the derivative control, and how these and how this effect of this offset and overshoot, these are basically reduced by introducing other kind of control actions also. So that's all from my side today. Was I clear in explaining this proportional control action?
Yes, ma'am.
Okay, if you have, so do you have any doubts?
No, ma'am.
Okay, fine. So then just I have already posted the instructions for today's quiz in the group, but just to give you a brief about that. So the quiz will be from 6 o'clock to 7 o'clock, and you will have, so it is, so we have created a Microsoft Forms. So once the assignment is shared with you, you have to go there, and there will be options are there in that Microsoft form, and you have to select your corresponding option. And make sure that you're like once you have completed all the questions, then only you press the submit button, because if you one person can submit your form only once. Okay, so make sure that you don't submit your answer before you have attempted all the questions or as much as possible by you. That is one thing. And the second thing is that after 7 o'clock, from 7 to 7:15, you will have 15 minutes of time in order to upload your the rough copy or the rough work of the solutions that you have done. That is there. But one thing is that keep in mind that 7:15 is that hard deadline. After that, it will stop accepting any kind of response. So you won't be able to, neither you will be able to submit the Microsoft form, nor you will be able to upload your rough work. Okay, so just keep in mind that 7:15 is the hard deadline. So you will have time from 6 to 7 for answering the questions, and another 15 minutes to upload your the PDF file of your rough work. Okay.
Ma'am, one doubt.
Yes.
The MCQ part also we can do till 7:15, ma'am. Like submission of rough note and the MCQ both before 7:15.
Yes, both before 7:15. But obviously, I would suggest that after 7:15, obviously, because we have made the changes in such a way that it will stop accepting any responses. Okay, but so you can say that 15 minutes is another grace time you have. So you have like overall 1 hour 15 minutes to complete to submit the form as well as the PDF. So an assignment has been created for the rough work also. Okay.
Ma'am, actually, yesterday we asked about how many questions will be there. Do you know now, or?
It's around 10 to 12 questions will be there.
Okay, ma'am.
Okay. So all the best for today's quiz, and I hope you will be able to, all of you will perform in a good way in the quiz.
One more thing, ma'am.
Yes.
All questions will be numericals. Will there be, I mean, because I have not focused much on theory, I have focused much on numericals. That's why.
No, theory as in, I mean, questions won't be subjective since it's MCQ. So obviously you won't.
No, ma'am. Like from the theory part, but in MCQ pattern, like regarding those control systems, what are the types of control systems, or regarding feedbacks, those kinds of questions, but in theoretical order,
mostly numericals. But then there might be one or two which require your concept, understanding of the concept.
Okay.
Okay. So if there are no more doubts, then we can end today's class.
Thank you.
Thank you, everyone. Yeah, thank you. Bye.
Thank you, ma'am.